Okay, let's get started. Welcome to Module 4, Lecture 4. We're going to pick up today where we left off last class. Last class, we were basically trying to complete our GPS story, right? We talked about identifying the satellite, then we talked about figuring out the distance between a satellite and our receiver. Then after that, we said, well, once we have all of the distances, we use the trilateration algorithm to figure out our location. But what if there's some kind of noise in the system, right? What if the trilateration equations that you get or the distance measurements that you get by doing cross-correlation aren't exactly accurate and have a little bit of noise? How do you solve systems of linear equations when there might be some small amount of noise present, or in the case where you cannot exactly solve the system? And that was the least squares algorithm that we talked about last time. And in fact, we derived this algorithm from scratch, right? We talked about how least squares is basically the projection of a vector onto a subspace. So just to remind everyone of where we were at, we had some system of equations, AX, and we say equal to B, but we know that this equal to is really an approximately equal to. We know that there's some error, and we know that this is not perfect. And we're thinking about a situation where A is not a square matrix, right? We're thinking about a situation when, in fact, A has this kind of shape. A is a tall matrix. So I have, let's say, an M by N A, and M is greater than N, so I have more equations than unknowns. This is sometimes called an overdetermined system. Right? Each row of A is basically a measurement or an equation, and the number of unknowns we have is basically the length of X. And this is much smaller than A. So X is, let's say, N by 1, and then B is basically the output of all of the equations. So we have M by 1 is the size of B. So when you're thinking about least squares, you want to keep this picture in mind, right? Typically, we've been thinking about when you have a square system, as an aside, if you have a square system, A is a square matrix. So A looks like this. And X and B are the same size, right? This is N by N, this is N by 1, this is N by 1, right? But this situation that we're looking up fundamentally is different from this square setup, right? And I want all of you to make sure you always have this picture in mind when you're thinking about overdetermined systems or cases where you have more equations than you have unknowns. When you go to upper division classes, such as, for example, 127 or even a little bit in 16B, you will be exposed to what are underdetermined systems. Underdetermined systems are systems where you have fewer equations than unknowns. We're not going to really talk too much about that in this class, except for a little bit. But here our focus is on this second case, which is how can you use the extra equations that you have to basically get rid of the fact that you have some noise in your actual measurements. So when we're looking at this kind of setup, right, what was the main issue that we had when we were trying to solve this? We were saying that, well, AX equal to B, A isn't square, and so we don't have really an inverse of A to be able to solve it the way we did in the square case, right? So A is not square, so A has no inverse, right? we were worried furthermore, which is that what is the space that AX can belong to? What is the vector space that AX can belong to? Well, A times any X can only belong to the column space of A, right? No matter what X you choose, A times X always belongs to the column space of A. On the other hand, vector B might not be in the column space of A, right? This vector B might be somewhere else. You might be in a situation where you have, this is the column space of A, and you have some vector B that clearly does not lie in this subspace, right? This plane is basically the column space of A, and the B is kind of sticking out. It's not in that subspace. And so what do we want to do? We want to say, well, AX is allowed to move around in this plane. It's allowed to move around in this column space. I want to find that point in the column space that is closest to this vector B, right? So does it make sense if I'm here to move this way to get close to B? No. Does it make sense to move this way? No. I want to move here, right? If I move to somewhat here, should I keep going? No, right? We discussed, we have this geometric proof that said that, well, how do I find the point that is closest? I find that point that is orthogonal, right? And I wanted to find, let's say, this vector z. That is the closest vector within the column space of A to the vector B. And what did we show that this z actually minimizes? So the orthogonal projection of B onto column space of A minimizes our error. And what is our error? Our error is the difference between AX and B. We want to be at B, but we can't get there. So whatever is remaining is our error. And we want to minimize the length of that error. Right? And here we're talking about it as minimizing the length of the error squared. But minimizing the square of a number and minimizing a number is exactly the same thing. So it doesn't make any difference whether I write a squared here or not. Does anyone have any questions about this setup or what is going on with this least squares? This geometry and this basic algorithm is fundamental. So I want to make sure that we're all on the same page with regard to this. I don't have time to fully redo the proof calculation that we did at the end of class last time, but I can take a couple of questions on this if people have questions. Yes? What does the magnitude of AX minus B represent? Good question. So this AX is this Z, right? This Z is this AX. So like we showed last time, this is this Z. And this vector here, does this orange look different than the pink? Kind of, you can tell. So this vector that goes from this orthogonal projection point all the way up to B, this is the error vector, right? This is, let's say, you can call this vector E. And Z plus the error gives me B. So AX minus B is the length of this vector E. What was the formula that we had? We basically had a projection formula, right? Our solution was to project B onto this column space. And this gave us that what we want for our x here, the best value that we have, which we're going to represent by x, I call this x hat. It's like vector x with a little hat on top of it, to say that this is our best estimate for what x should be. This is A transpose A inverse A transpose B. And Ax hat, which is what this quantity is basically A times x hat. So A times A transpose A inverse A transpose B. So last time after class I got a question that I think was very good, which said that, well, when you look at this A transpose A inverse A transpose B, can't we cancel something? Because, there's all these, they're all super similar. But we can't, unfortunately, because what are the dimensions of this thing, right? A transpose A, what is the dimension of A transpose A? A is m by n. So A transpose has dimensions n by m. A transpose A has dimensions n by n. Right? So this is a square matrix. We can't really separate this out. This inverse holds only for this square matrix A transpose A. You can't say that, well, let me take the inverse of A transpose times the inverse of A. You can't take this inverse inside these parentheses. Okay? That's really important to notice and realize that some of these operations that you're really used to doing when you're dealing with real numbers or scalars don't really work with matrices. We can only take this inverse here because we're thinking of A transpose A as this square matrix, right? So A transpose inverse doesn't really exist because it's not a square matrix. Inverses only exist for square matrices. Okay? So, any questions about this? I'm going to just pause and, take a second, ask me questions, or ask your neighbor questions. I'm just going to wait. Yeah. Is x hat the direction of our projection? I wouldn't think of it really as the direction per se. Our projection is basically this vector z, which is ax hat. Yeah.
So where does x show up in our diagram of this?
Where does x show up in our diagram? Great question. X does not show up in our diagram here. We don't have a picture for where x is. X has no restrictions on being part of anything, any particular space. But we know that A times x must be in the column space of A, by definition, right? So, good question. X does not show up in this picture. This pink arrow is A times x. Other questions? Yes? Yeah, good question. Where does x hat fit into our picture? So x hat is sometimes called the best estimate of x. Why do we call it x hat and not exactly x? This is just a question of terminology. No one would fault you if you were to just say x is equal to this. But we're saying this because we know that A times x hat is not exactly equal to B. We know that AX is only going to approximately equal B. So that's why we separate out this idealized x, which doesn't exist, but if it did exist, AX would be exactly equal to B, and x hat, which is our best estimate of what that actually is. Does that make sense? So this is just notation. If the notation is confusing, feel free to just call these things x's, you know. It won't really matter, but I just wanted to introduce this because you might come across this somewhere and you should be familiar. Usually when people put a hat on something, they mean they're making an estimate of that quantity. They don't have exactly the value, but they're making their best guess. Okay, so let's do an example, and hopefully that'll, you know, start to get more juices flowing. So let's think about the following example. I'm going to do a simple one. You're going to do some more complicated ones in discussion tomorrow, on Monday. So make sure you go to discussion if you want a chance to practice this more. Let's say A is this simple 2 by 1 matrix. So A is 2, 1. And B is equal to also this 2 by 1 matrix. And I have A times X is equal to B. So X in this case is just a scalar, right? It's a 1 by 1 matrix, essentially. So I can write 2, 1 times X. This is just 1 by 1 times 1, 1. Right? So I have this AX equal to B. And, you know, if we were to try the things that we've learned in Module 1 so far, what would we want to try and do? We have a system of linear equations, right? Hopefully by now you have some kind of default response that says when you see a system of linear equations, apply Gaussian elimination, right? So it's something that's really worth trying, right? So let's just see what happens if we do our natural, you know, autocorrect response to a system of linear equations. So, does Gaussian elimination work? So, let me make the augmented matrix. 2, 1, 1, 1 is the augmented matrix in this case. What does this give me? Well, I make this a 1, make this a 1/2, this is a 1 and a 1, just by multiplying the first row by a half. And then this gives me 1, 1/2, 0, 1/2. Right? So what do I have at the bottom? I have a row of zeros. And what are they equal to on the right-hand side? A non-zero. So what does this mean for our system? No solutions, right? So what does this say? This says that, well, there doesn't exist an X that perfectly satisfies both of these equations. Right? Because they're noisy equations. You don't have an X such that 2 times X is 1 and 1 times X is also 1. But what do you do? What if you get such an equation out of your system of measurements? You have, this is what your imaging system gives you, this is what your trilateration system gives you. You know, you have to produce an input. You have to tell the user, well, you know, these are the measurements I got. There's no perfect solution, but I better give you something. How do you solve this situation? This is where now least squares can come in. So, let's try to use least squares, right? And we can write, let's say now we can try our x hat is equal to A transpose A inverse A transpose times B. Okay? So what is A transpose in this case? A transpose is a row vector, right? And it's going to be 2, 1. So A transpose A is equal to 2, 1 times 1, 2. 2, 1 times 2, 1. Right? Why don't you go ahead and calculate this quantity out? Just go ahead and do this calculation. Plug in A transpose, plug in A, take the inverse. Just do that calculation out. Take a minute and do it. Check your answer with your neighbors. How many people are done? How many people want another minute? Okay, another minute. You can talk, Make sure you understand what's going on. If you're confused about something and you don't want to ask in the whole class, ask your neighbor. Everyone turn to your neighbor and make sure they understand. Ask them if they are okay. If you're talking to neighbor on one side of you, make sure the neighbor on the other side of you isn't feeling left out. Okay, so how many people are done now? How many people have an answer? Most people have an answer? Okay. So, can someone tell me what A transpose A comes out to be? It's exactly 5, right? 2 times 2 plus 1 times 1. Right? It's a 1 by 1 matrix. So, A transpose A inverse is equal to 1 over 5. So, X hat now is equal to 1 over 5 times 2, 1 times 1, 1. 2, 1 times 1, 1 is what? 3. So X hat is 3 by 5. Does X hat equal to 3 by 5 perfectly satisfy the first equation? Does it perfectly satisfy the second equation? No. But what it does is it approximately satisfies both equations. And what it does is it says that this quantity, ax minus b, is minimized. So if we draw a picture of this, for example, let's say I have, so a is basically 2, 1, so 1, 2, 1, 2, 2, 1. This is my A. And my B is 1, 1. This color doesn't look very different. Right, this is my B. And this is my A. So what we're saying is how much should I walk along this vector A so that I can get to B? Right? Is this a reasonable question to ask? Kind of, but not really, right? There's no way to get to B by just walking along A. So you're saying, well, if I'm only allowed to walk along A, where do I want to stop? Well, I want to stop here, at this point of the orthogonal projection. Right? And so this point is exactly 3/5 times A. Okay? Does everyone get how this geometry and the algebra are playing together here? And have a sense of what this is doing? So, I encourage you to just try and make up some examples like this and try to do it on your own for simple 2x2, 3x3 cases. And it'll give you some practice and hopefully help clear things up a little bit. And you'll get a lot more practice of this in homework and discussion. But now that we have some basic understanding of least squares, I want to really talk about, where and how we can really use the least squares algorithm and why it's such a cool algorithm. We can definitely use it for the trilateration example, and you will be doing exactly that in lab. So I'm not going to do exactly the same calculation out here. You'll get a chance to do it in lab. But there's many, many, many powerful applications of least squares. And so I wanted to start with actually the first one. Can I split the screen to have my computer and the doc cam? So, this planet, or what is called a dwarf planet, is called Ceres. And this body, I guess, lies in the space between Mars and Jupiter. And understanding the motion of this particular planetary object, it's been classified from a planet to an asteroid and from an asteroid to a dwarf planet over the years. This is one of the first known applications of the least squares algorithm. We studied Gaussian elimination in this class, and Gaussian elimination is called Gaussian elimination because one of the people to widely use it first was the mathematician Gauss. Of course, Gaussian elimination wasn't invented by Gauss. It was invented, it was well known in China far before Gauss. But least squares, again, we don't know exactly who invented it, but it's definitely true that Gauss was one of the mathematicians that used it a lot. And in particular, the most famous, or one of the most famous applications of least squares, and one of the first documented ones, was when Gauss used least squares to be able to predict the path of this object series. So this story actually takes us back to 1801. January of 1801, there was an astronomer called Piazzi. Yep. Not making it up. And he was observing the skies, as astronomers tend to do, and he made observations of, a point of light in between Mars and Jupiter, or in the skies where he would, in between the space where he would expect that there would be blank space between Mars and Jupiter, and he made 22 observations of this over a course of many, many nights. And, there had been people who had been studying the solar system, obviously, and people were there was an expectation that the gap between Mars and Jupiter is kind of larger than what was expected. So people thought it would be natural to have another planet there. And so when people thought that, maybe here's a planet that is that missing planet between Mars and Jupiter, they saw this little point of light that was basically moving across the skies at night. People got pretty excited. And then Piazzi got sick and stopped making observations of this planet. And then the path of the planet actually disappeared behind the sun. So it was being tracked for a while, then Piazzi fell sick, and then, it was behind the sun and people couldn't really see it anymore. And so then what was done was actually these observations that he made were published in a scientific journal where they said, well, we really think that this is the missing planet between Jupiter and Mars. astronomers around the world, here's the observations that we've seen so far. Can you try to figure out where the planet is going to be next? Because we can't see it now. We can't search the entire sky for this planet. We have to figure out kind of where to look to have a reasonable certainty that the planet that we see is actually what we're looking for. So these first observations were, I believe, sometime in January of 1801, and they were published in June. And this is when Gauss entered the picture. And what he did was he actually used a variant of least squares to be able to make these predictions and figure out exactly where the planet was going to reappear. And turned out there was many astronomers who tried to make predictions for where this planet was, but his technique turned out to be by far the most accurate. And so what did he do, right? At that point, Kepler's laws were already known. And he used Kepler's law. What does Kepler's law say? Kepler's law says that basically planets will orbit the sun in an elliptical orbit. And so Gauss used the fact that, well, if this is going to be a planet, and if it is indeed orbiting the sun, then it should actually be following an elliptical path. Of course, there can be many different elliptical paths that it could follow, right? In fact, every single one of the planets follows its own unique, different elliptical path. How do you figure out which elliptical path this is? And this is where the least squares technique comes in. So, what we have is, let's say we are, in 1801 with Jupyter notebooks and have a little bit of fake data to play with. This is not what they did. This was done way before computers. Every single calculation was done by hand. It's really mind-blowing what people managed to accomplish. We're going to do it the cheap way with just using a quick laptop simulation. But let's say what we had was a bunch of XY pairs in the plane, right? For observations where we have actually seen this particular planet. This is our data, right? In a machine learning context, one might think of this as training data. We have some XY pairs that are given to us. We want to predict future paths of this given this data, right? And so I have this planet data and I can, plot it. And I want to say, let's say I've observed this over time and I want to figure out where here exactly I can actually make a prediction. But how do I go about doing this, right? How is this even connected to least squares? Right? We can do this, and I'm telling you we can do this, but there's a bunch of steps between how to start doing this and where to go. So for this, first we should say that we know that the planet will have an elliptical orbit. Okay? And we know what the equation of an ellipse is. So if I have these XY pairs, I know they're basically following some path such as ax squared plus by squared plus cxy plus dx plus e equal to 1, right? This is just the general equation for an ellipse. Right? So every one of these points, we think, should satisfy this equation. So we have some information. We have this model, effectively, of where we think this data is coming from. And we want to basically identify what the model is in order to be able to make a prediction. So when I look at this equation, what do we know? What do we not know? Is this a linear equation? Can I just use Gaussian elimination somehow to magically produce what I want to do? Take a minute to think about this. Think about, assuming you know this, assuming you have this data, how can you try to put this together to make this into a problem that is actually solvable by the techniques that we've thought about so far? Just take a minute to think about it, and then we'll do it together. Feel free to talk to each other, discuss. If you were talking to the neighbor on your right the last time, make sure you talk to the neighbor on your left. We want to make sure everyone in the class feels welcome and included. So how many people have some kind of maybe idea? Does anyone have an idea that they might want to share with everyone on how to proceed? Someone who hasn't spoken yet, yeah. Yep, can we somehow use our data points to generate a set of linear equations that we can solve, right? That's the idea. And how do we get about this idea? So let's look at this equation, right? What do we know? What do we have given to us? We have, let's say, these pairs of points, x1, y1, x2, y2, so on and so forth, right? Do we know exactly what the equation of this ellipse is? We don't know what this equation is, right? So what are the unknowns? The unknowns are the coefficients A, B, C, D, and E. I want to find the equation of this ellipse. The equation of this ellipse is defined by its coefficients, right? So when I look at this equation, is this equation linear in x and y? No, it has quadratic terms, right? But is it linear in A? It is linear in A, it is linear in B, it is linear in E, it is linear in all of these things. And turns out that is linear in the stuff that we don't know. And it has some nonlinear quadratic terms. But we have a data set that gives us what x and y are. So we don't need to, the fact that there are some quadratic terms there doesn't bother us at all. So what we're going to do is we're going to set this up now as a least squares problem. So I'm going to write my vector of unknowns. Which is basically A, B, C, D, E. Okay? And I'm going to try and write this now as a linear equation. So let's say I have my vector of unknowns here, A, B, C, D, E. A gets multiplied by x squared, right? So let's say I have this data point x1, y1, and I plug it in, that gives me the equation basically ax1 squared plus by1 squared plus cx1, y1 plus dx1 plus ey1 equal to 1. And remember here, x1, y1 are all known. So now I can write this here. If I want to try to do this, I can say x1 squared, y1 squared, x1, y1, x1, y1. Right? My first data point makes up the first row of a matrix here. If I have a second data point, can I write a second equation here for x2, y2? Right? So I can write x2 squared, y2 squared, x2, y2, x2, y2. And if I have n different data points, I can write xn squared, yn squared, xn, yn. And now I want to write this as equal to something. What is this equal to? Yeah? Should what? Why would it be that? Because I'm taking y1 times e. And so, no, I don't think so. Where? Oh, it should be EY, sorry. That's just a typo here. Right? The equation of an ellipse, so, is symmetric in x and y, right? You have a quadratic term in x, quadratic term in y, the cross term. Linear term in x, linear term in y. This is e times y. This is just a typo. But since you're thinking about a column of ones, what's the thing that's going to go on the right-hand side? Column of ones, right? So now I have a linear equation. I have basically, this is my matrix A. This is my unknown vector x. This is my vector B. So let's actually do it. So I have this, and I'm gonna now, build this A now, right? And what am I saying? I'm saying basically take the x component squared, the xy component, the y component squared, the x component, and the y component, right? That's what this A is being made up of, and I'm just stacking them up. My B, as we talked about, is just a column full of ones. And then I'm going to do least squares on this. I do least squares, I get my x out, and I expect x to have length 5, so I pull out all of the entries of x. And then I look at A times x, right? Because remember, if I want to find the approximation of vector B, right? And A times x is the approximation of vector B. What is vector B? We expect B to be a vector of ones. So if I take this x that I got out of the least squares equation and I multiply it by A, what do I get here? I'm hoping for a vector of ones. What do I actually get? I get an approximate vector of ones, right? So this is not going to give me the exact solution, but it's pretty good. And then I do some code to plot stuff, and that's something, it's not very interesting. But then basically plotting this equation, what do I get? This is basically using what we figured out. We're basically plotting the equation of the ellipse using these least squares solutions to plot this blue curve. And as you can see, The red points aren't exactly on the curve, but this is a pretty good prediction. So if you were to predict where the planet would be, you would probably predict that it's going to move along this blue line. And that's a pretty good way to do it. So this, believe it or not, like really think about this. This was done in 1801. Right? We talk about machine learning as though it was invented today. But this was done in 1801 without any computers, and this basic fundamental mathematics is what really forms the heart of a lot of the algorithms that we're building out today. So when we have a matrix like this, where we have these this column of x squared, this column of y squared, in machine learning jargon, these are often called polynomial features. So if you take classes like 127 or 189, you'll encounter this terminology. We're not going to go into it very much in this class, but you should know that you're learning the fundamentals for a lot of major modern algorithms. Okay, so any questions on what just happened? And pause for a minute. Is everyone with me here? Yes, question.
So it wasn't an issue that x and y were square in the equation because those were known?
Exactly. It wasn't an issue that there were squares because we basically computed those values, right? If you look at the code here, I guess here I can even print A, right? Just add a cell and say A. Right? These are basically the values. This is the first column of this matrix A is all x squares, but they're numbers because we know those data points. Yeah.
So is the idea behind having more equations when necessary, like if we have 22 versus just a bare minimum of 5, we have a more accurate listing?
Exactly. If we have more equations, then we are not going to be super affected by a particularly bad noise realization on a particular point. You might have heard of this term called outliers. Outliers are sometimes when you have a lot of data points and some points don't really follow the trend. And you sometimes don't want these to affect your model terribly. So if you have more points, these, weird points can be ignored and won't affect your model too much. Of course, how to really do this is a full, series of multiple courses all the way up into grad school. We're not going to go into all of that in this class. It's out of scope. Yeah. So it's possible that you will have, it's possible to have good and bad properties of data. There's also notions around how to think about whether your data is good or not. Right now, we're not going to think about most of this. When you go to upper division classes, you'll learn about things like condition numbers and things like that, and that'll help you understand those questions a little bit more. Yeah. But that's completely out of scope for us right now. So next year, you'll figure it out. Other questions? Okay. So now we've done this problem where we've thought about, fitting an ellipse to data and trying to predict using this quadratic equation, essentially. But if we can do this for a general quadratic equation, we can probably do it for a lot more other kinds of polynomials, right? This same trick will work. And this brings us to linear... Oh, no, sorry, I still want to use that. Sorry. Linear regression. So how many of you have seen a plot like this sometime in your life? There's a, question? You've seen this plot before. Very good. So let us step back for a moment and study exactly what this plot is saying. What is the x-axis on the blue plot? It says how long you've been awake. The y-axis says, well, how good is your performance? As you're awake for longer and you don't sleep, what happens to your performance? It has a negative slope. What does this suggest about what you should be doing the week before or the month before or the year before an exam? You should be sleeping. Don't stay up all night and don't get sick. But as you can see, what this plot is showing in particular is that, in fact, you can also compare, blood alcohol concentration to performance. What kind of curve do you see there? In fact, you can see that both these curves are quite similar. But when you look at this, you might have heard people talk about these kinds of graphs and say that, there's a linear trend, right? And, let's try and understand what this trend is. And how did people, when someone writes a scientific paper like this, where does this line come from? How do they know to draw this line and not a slightly different line, right? There's different lines that could potentially fit this data. Why did they pick this line? This line is coming from least squares. And so now let's figure out exactly how we can do a linear regression problem using least squares. So we have, let's say, some data. I have some points here, and I want to figure out, what is the trend here? This line, or this line, or this line. Which line am I supposed to pick? So what is the equation of a line? I know that y is equal to m times x plus c is the equation of a line, right? And I want to find, let's say, the trend. And so I'm given basically data points, x1, y1. x1 is, let's say, how long you slept. y1 is your performance. x2 is another day how much you slept. y2 is the performance related to that. So on and so forth, right? You have xn, yn. You have all these different data points. Can we use the same idea that we did for the ellipse here? So now I have, again, what is known to me here? The x's and y's are what are known to me, right? This is my data. If I want to figure out the line of best fit, my m and my c are my unknowns. Right? Find the line of best fit. Right? So now I can say, well, y1 is equal to m times x1 plus c1. y2 is equal to m times x2 plus c2, and so on. I can make now a vector of my unknowns, which is mc. And I can write this again as a matrix equation where the first column here is x1, x2, xn. The second column here is going to be a column full of ones. And this is going to be equal to y1, y2, all the way up to yn. Yeah?
So why are there different C's?
Why are there different C's? There aren't. There's only one C. Oh, sorry. I apologize. Good point. This is just... There's only one C. There's one slope, one intercept. Right? So I have y1 is equal to mx1 plus c, y2 is equal to mx2 plus c, and so m times x1 plus c is equal to y1. I'm just rewriting these equations in matrix vector format. This now becomes my A matrix. This is my x vector. This is my vector B. right? So let's say I do an experiment, I gather a bunch of data points, and I want to figure out what is the line of best fit, I'm going to put them into a format like this. And the M and the C that this is going to pop out, that least squares is going to pop out, is what is going to give me the line that is the best fitting line. Yes, question? So that will give you basically M and C, right? X will give you M and C. So now if you want to actually draw the line, you actually have to plot this line, right? Yeah, the answer, basically, once you have the M and C, you can plot things or represent them in however you want. Yeah. Okay. So another place where people really, really want to, take data and analyze trends, as you can imagine, is not just in scientific studies, but in particular, people want to analyze things in the stock market. People really would love to be able to have a great prediction algorithm for what the stock price of a particular, company is going to be tomorrow, day after, 2 weeks from now. If any of you knew exactly how to do this, you probably want to start a company soon. But this is a pretty hard thing. We know that we're not particularly good at this. But again, when people talk about making financial models, when people talk about modeling prediction, are they doing exactly least squares? Probably not. But are they building on the fundamental principles of least squares? Almost certainly yes. So here what I'm showing is, this is actually a plot of the Facebook data stock at some point, I think in 2016. And this is the stock price. I forget exactly what the months were for this. But if you wanted to predict what the price of the Facebook stock was going to be, one thing that you might reasonably want to do is you might say that, well, this kind of looks like a linear trend. Let me try and fit a line to it. And so what this code is doing here is it's basically saying, well, let me make my A matrix. This A matrix has the first column, which is the axis here. And this is just the time of when I am looking at the data. The second column is just a column of ones, because that's how we have set it up for a line. And the B vector is actually the stock price on that particular date, right? So the X is the date, the B vector is actually the stock price, just given our equations. Does everyone see how this is exactly mapping to those equations? Then I can call basically these squares on this, and I can say, well, now if I want to basically figure out what this line is, I'm going to take the M and the C that my least squares algorithm recovered and plot this line. And this is the line of best fit I get. And maybe I could extrapolate that, okay, if I have this line, I can say, well, what is the prediction at, day 61, day 62, day 63? Maybe it's going to be points exactly along this line. Do I know this for sure? Probably not. Do I suggest any of you do this? Definitely not. But it's worth exploring, right? So here's another graph. This is actually looking at Snapchat stock prices. And as you can see, this was in the past year. So as you can see, there's like some part of a linear trend, and then maybe not so much of a linear trend. So I could try to fit a line to this, but it's doing a pretty bad job at prediction, right? It's not doing as good of a job. So maybe this is something that, is really not something exactly that one wants to do. I'm not going to go into the details of how we're doing this here, but you can see that, this is kind of a line, but maybe it's not really a line. Maybe it's better predicted by a higher degree polynomial or something else. Maybe I want to use some other kind of model. So I have this data here. And what this function is doing is it's basically saying, well, maybe I can, instead of fitting here, we set it up so that we're fitting a line, right? But as you saw with the ellipse, we could set this up so that we're predicting with a quadratic. That was a bivariate quadratic. We could use a univariate quadratic in this case. We could use a cubic. We could use a quartic equation. We could use all kinds of things. We could use, cosines of the data points or sines. We could use many, many different kind of transformations and use this same trick. And this trick is used all the time in all kinds of machine learning algorithms. So what I'm going to do here is that, well, if I say that I want to predict with degree 1, this is the line that I get, and, it's something. But let's say I wanted to try and fit a quadratic equation to it. Kind of does a lot better, right? So maybe there's some kind of quadratic trend going on around here. Well, let's see what happens as I extrapolate this out. This is my quadratic prediction. This is my actual stock price. Again, do I recommend you do this? No. But it's kind of fun to play around with and kind of interesting to try, right? So it gives you a sense for when people talk about doing financial prediction or any kind of prediction using any kind of data. They're not doing exactly this, but this is really the spirit of the kind of thing that they're trying to do. Any questions on any of this so far? Okay. So now that we've seen some cool applications and we've decided that we're not going to try and get rich quick, let us go back to getting rich the usual way, which is by doing a lot of mathematics. Could I have both the doc cams back, actually? Thank you. So we have this least squares algorithm. This least squares algorithm is obviously quite powerful and can be used for a lot of different things. But we had this caveat that we talked about last time, right? We had x hat is equal to A transpose A inverse A transpose B. And we said, well, A transpose A is a very nice square matrix, but does that mean that we can always invert it? No, right? A transpose A might not be invertible. And how do we get around that? Like, what happens to the least squares algorithm? And fundamentally, least squares can fail if A transpose A is non-invertible. So we want to understand, really, what cases give us this situation where A transpose A actually doesn't have an inverse, right? We want to understand this a little bit better because that tells us when our algorithm is going to work and when we're going to say, well, we plugged it in and basically Python's going to give you some kind of error. And it's going to say that, well, this isn't actually invertible. I cannot actually give you the least squares estimate. So if a square matrix does not have an inverse, if A transpose A inverse does not exist, this basically we know is the same as saying that A transpose A has a non-trivial null space. Right? Back in module 1, we had all these properties that talked about invertibility and null spaces, and we saw that, well, the ability to invert a matrix is connected to whether or not a matrix has a null space. And now what we're going to see is basically the following theorem, is that the null space of A transpose A is equal to the null space of the matrix A itself. And so just by looking at the matrix A, we can actually tell whether or not our least squares algorithm is going to work. We don't have to compute A transpose A to know whether or not our least squares algorithm is going to work. Our measurement matrix A has all the information. And remember, what does it mean for, let's say the null space of A is non-trivial, right? The null space of A is non-trivial means that there exists some A times some vector, let's say vector Z, such that A times Z is equal to 0. Right? And Z is not a 0 vector. If only the 0 vector satisfied this, then A would have a trivial null space. But because the null space is non-trivial, there's a non-zero vector Z that satisfies this equation. Okay? But what this means is that basically the columns of A are linearly dependent, right? So this means that the columns of A So by basically looking at whether or not these columns are dependent, or linearly dependent, we can figure out whether or not A transpose A is going to be invertible. But now, before we explore, when this can fail, and I'll hopefully get to an example at the end where we can see exactly how least squares might fail, let's actually go ahead and prove this theorem. Okay? So if we want to say that two null spaces are equal to each other, when we have these equal proofs that involve equality, right, there's two things that we always need to show. We always need to show, first, that let's say V is a vector that belongs to the null space of A. If V belongs to the null space of A, then we want to show that V must belong to the null space of A transpose A. Right? And second, we want to show that if W is a vector that belongs to the null space of A transpose A, then W must belong to the null space of A. Right? These are the two things that we want to show. If we just showed the first, why is showing the first not enough? It doesn't give the equal, right? It says that, well, if V is in this set, then it also must be in this set. So that means that one is a subset of the other. But it doesn't show equality. This also shows a subset relationship. And so you want to say that everything here is in here, and everything here is in here, then the two must be equal, right? But if everything here is also in here, this might have other things that are not in here, right? So that doesn't show equality. To establish equality, you need to show this both ways. Okay? So, take a minute, try this on your own. I'm not going to give you the answer right away. Part 1 is easier than part 2. So start with part 1. How many people want to start working together? Few people. How many people want to work on their own for a little bit more? Some people. Okay, take a couple more minutes. For those people that are stuck, the number one thing that I see as people getting stuck is not writing stuff down. This is kind of a very common failure mode. Like if you're starting to do something and you're not sure, don't be afraid of putting something on the paper. It doesn't have to be right. It doesn't have to be perfect. But just write stuff. It'll help you. If you have an if and then a then, write out what that if means. Write it out mathematically. Write out what the then means. Write it out mathematically. Okay, in the interest of time, let's start working on this together. So, let's look at the proof part 1, right? We say if V belongs to null space of A, then V belongs to null space of A transpose A, right? So let's say V belongs to null space of A. What does that mean? What's the first thing you want to write down? Yeah? So you have some V, A times this, let's say V, is equal to 0, right? Where do you want to go? You want to have A transpose times A times V equal to 0. So I want to have A transpose times A times this exact V is equal to 0. How do I get here from here? Multiply by both sides by A transpose, right? So multiply by A transpose. This gives me A transpose times A times V is equal to basically A transpose times 0 is equal to 0. Which proves exactly what I want, right? It gives me exactly what I want. Therefore, V belongs also to the null space of A transpose A. Right? Pretty just straightforward, right? Just write both things out, see what's similar about them, and try to move forward, right? Everyone's clear on how we did this? Any questions here? Okay. What about part 2? Right here, I want to say that, well, W belongs to null space of A transpose A. So that tells me that A transpose times A times W is equal to 0. What do I want? I want to look at this AW, right? A times W, and I want this to be equal to 0. Does everyone understand why A times W this is what we want, that AW equal to 0? Yeah? I want to really make sure that everyone's with me here. I'm willing to stop. Okay. So here we had this nice trick where we could just multiply by A transpose, and we kind of easily got what we wanted. But that same thing somehow doesn't work, right? Like I don't have this, I don't know this, so I can't multiply this by A transpose. I want to somehow derive this. All I have is this equation. But here what I'm going to do is I'm going to look at this quantity and try to start playing with it. So say, consider A times W is equal to some vector Q, right? Let's call that vector, whatever A times W is, let's call it Q. Okay? What I really want is I want Q to be 0. I don't know that yet, but I really want it to be 0. So I'm going to start exploring this Q vector. What is one thing that I know if Q was 0? Yes, question.
If you want something, why can't you start from the one part and get to the original part? Why can't you work backwards and use the same code you use the number 1 to prove that W is the
The good question. Why can't I start here and prove it here, right? Because that's saying that if this is true, then this is true. But the implication is the other way around. So you have to be very careful. When I have if and then, I can assume this to prove this. So because I have if W belongs to null space of A transpose A, then this, I cannot start from here. I can't assume this because that's what I want to show. Right? This is a really good point. This is a subtle point. Please, everyone, make sure you understand why we cannot start from here. We're saying, if this is true, then we want to show this. We can't assume this part. Okay? So we have A times W equal to 0. Let's consider this Q. If Q was the 0 vector, what would the norm of Q be? It would be 0, right? So now, what if I considered this quantity? The thing is that here I have something that has this transposey thing, and I have something that has multiplications with something like Q. So let me just play with it to consider this Q times Q. What is Q times Q? Q times Q is basically A W transpose times A W. But this is basically equal to W transpose A W. Right? This transpose can go inside and it flips the arguments. So I have this, but what is this equal to? Let me be very precise here. W transpose A W. What do I know about this? A transpose A times W. What do I know? This is 0. So this is W transpose times 0. So this whole thing is 0. So the inner product of Q with itself is 0, which means that basically the norm of Q is 0. But if the norm of a vector is 0, then Q must be equal to 0. And as a result, we must have W belongs to the null space of A. Right? So this is a different kind of proof from what you've seen before. It's a little bit more subtle. Right? This is a slightly more advanced proof than what we've done in Module 1 so far. But make sure you understand this. If this is confusing, please come to office hours. What we see here about how invertibility can sometimes break least squares, we'll pick up with an example next time.